Miss. All right, so we're doing 2-8, which is two variable inequalities. We did inequalities in chapter 1 where we just had the x and we solved for x. This time we're going to have two variables, so like an x and a y, and we're going to deal with graphing two variable inequalities, which is our learning objective, is to graph two variable inequalities. So graphing an inequality in two variables is similar to graphing a line. The graph of a linear inequality contains all the points on one side of the line and may or may not include the points on the line. So we're going to graph lines and everything either on the line and above or on the line and below or just above or just below the line is going to be our solution. So we're opening up the possibilities of solutions. All right, this is where you guys are going to start writing. Make it a little bit bigger. A linear inequality is an inequality in two variables like x and y. So if two variables is freaking you out, just put x comma y, whose graph is a region of the coordinate plane bounded by a line. I want you guys to circle the word region. So before we were in one variable, we were solving and getting values of x. In this case, we're going to get whole sections of our graph that are answers to our inequality. This line is the boundary of the graph, and you don't actually have to write after this. So starting with, because we are going to draw this picture. So this picture will take care of the boundary and the half plane. So instead of writing this line as the boundary, just draw the picture and point to the line that's the boundary. If you already wrote it, then yay for you. You still have to draw the graph because picture's worth 1,000 words, right? So the boundary separates the coordinate plane into two half planes. So your line cuts your graph in half and you get a half plane. One of those half planes is going to be your solution to your inequality. The other half is not the solution. So I want you guys to go ahead and draw this picture right here. We can either have, when we have a dashed line, then our solution is not on the line. When we have a solid line, our solution is included on the line. So dashed is not included, solid is included. Alright, so I do want you to have the definition for test point in your notes. So because I'm going to ask you in the instructions to do this, and if you don't even know what it is, then we're in trouble. A test point is a point that you pick on one side of the boundary of the graph. If the test point makes the inequality true, then all the points on that side of the boundary are solutions. If the test point makes the inequality false, then you are on the wrong side of the boundary line and all the points on that side are not solutions and the ones on the other side are solutions. And we're going to see how that works. We're going to graph these two inequalities. And we're going to pick a test point and see if we have graphed it correctly. The first inequality we're going to look at is y greater than or equal to negative 2x plus 1. So step number 1 is graph the equation as if it were y equals negative 2x plus 1. We are going to graph the line. So I'm going to graph this using slope intercept. I know my slope is negative 2 over 1, and I know my intercept is positive 1. So I'm going to start on my graph at positive 1. And I'm going to go down 2 over 1, all the way across my graph. And then I'm going to follow that same pattern the opposite direction so that I've got a nice clear line rolling out. Because I have it's greater than or equal to, so I'm graphing this. Because I have a greater than or equal to, I need a solid line. So I'm going to go get my line making tool. That could be a ruler or a piece of paper or the edge of your calculator. Whatever line making tool makes a straight line that you're going to use, go ahead and get that out. I'm going to make the line green to go with my coordinate points. And it's going to be a solid line. It's solid because it is equal to. So everything on the line is also a potential solution. Okay, so I graphed my line. So now we have to decide which half of this boundary we're going to shape. So I'm either going to be up here or down here. I'm going to look at my inequality, and it says y's, all my y's bigger than negative 2x plus 1. So if you put your pencil on your line, if you put your pencil on this line, everything above that line is in our solution region. So we're going to shade everything above. So step 1 is graph, step 2 is shade, and then step 3 is test a point. So I'm going to pick the easiest point I can find within my region. I don't want to go like up here to, I guess 10, 10 would be okay, but I like something that has a 0 in it, and then something that is definitely in that region. So I'm going to test the point 3, 0. If I have done my shading and my graphing correctly, then 3, 0 should make my statement true. So I'm going to go y is 0 and x is 3. So is 0 greater than or equal to negative 2 times 3 plus 1? Negative 2 times 3 is negative 6. Negative 6 plus 1 is a negative 5. Is 0 greater than or equal to negative 5? Yes. So that checks out, and I know that I have the correct graph here. So when you guys are taking your chapter 2 test, when it's asking you to graph the inequality and show that it's your shading is correct by using a test point, this is what I want to see on your paper. I want to see you pick a point in the region and show me that it works. Okay, so let's follow these 3 steps with B. So B is y less than negative 2x plus 1. Thank goodness, it's the same doggone equation. So we're going to graph y equals negative 2x plus 1. And he has the same slope and intercept as we've already graphed. Go ahead and get that on. But in this case, we are going to go dashed line because we cannot equal the way I do a dash line when I'm writing it out is I put my ruler down and I just go dash, 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 dash. And then if I forget, because I'm really excited to graph stuff, I just erase parts of my line so it makes dashes. So that I've done that many a times. Because I'm super stoked to graph it. I'm like, I know how to graph a line! And then I get a solid line down there and I look back and I go, oh, it's not equal to, so then I erase sections of it to make it look dashed. Okay, so we have to evaluate, are we going to shade above this line or below this line? So I want y, if you look at the inequality, I want y values that are less than our line. So I'm going to grab my highlighter. We'll make this a nice shady orange. And I'm going to start at my line, and then I'm going to shade everything below. You follow the inequality. This inequality says all my y values smaller than the line. So that means lower. Why is everything down below? Yes, sir.
So if it was a positive, like the opposite, would you still shade the left side, or would you? So you just anything that's kind of like below it.
Mm-hmm. So you. Then there's nothing above or below. It would be x equals if it was a vertical line. So in that case, I have never seen a situation in this genre where we're shading y greater than or equal to. If it's got y in it, then it's going to be the two variable inequality. If it doesn't have a y, then it doesn't exist in this realm. Good question, guys. Okay. So those of you guys who are looking ahead and going, oh, we have a portfolio discussion coming up, and I need to start collecting some word problems. This happens to be a word problem. So how do we use linear inequalities? This is actually the part I really love, because you can use them to make sense of life. Let me pull this guy in a little bit. It went off the page. Okay. The map shows the number of tickets needed for small or large rides at the fair. We are going to decide that we want to spend no more than $30 for tickets. What are the possible combinations of small and large rides that you can ride now? Use a graph to find your answer. So we are going to take and collect this information. So a small ride is 3 tickets.
That's to write the part.
Yeah. But I want you don't have to draw the picture, you just say small ride is 3 tickets.
And
Large ride. Yeah. You don't have to write the map shows, you just have to write small ride is. And then you spend no more than $30 for tickets. Just the essential information. Otherwise, when you look back at this, you will say, I have no idea what I wrote down. Large ride is 5 tickets. Tickets are 25 cents, and since I live in 2016, I'm going to write that as $0.25. I'll give you guys a second to write. So let's use S for small ride and L for large. Actually, no, we didn't even do that. Sorry. I'm with you. Okay, so small right is S, large right is L. And tickets are 25 cents. So, on our graph, we have to decide what's the dependent and independent variable. So we want to know tickets versus money. Tickets versus money. Which one do we put on which axes? Which one usually goes where?
I do the tickets on the bottom and money.
I would do tickets on the bottom and money because the amount of money you spend is dependent on the number of tickets you're gonna. Right. Right. Okay, so to recap, S is the small ride, is 3 tickets. L is the large ride, it's 5 tickets. S is 3 tickets times 25 cents. So all of the cost to ride one small ride is 75 cents. L is our large ride. We multiply that by 5 because it's 5 tickets. Each ticket's 25 cents. So it's $1.25 to ride a large ride. Now we put our inequality together. We take our number of small rides, multiply it by 0.75, plus our number of large rides multiplied by 1.25, and that has to be less than or equal to our $30 budget. So now we're going to let's put S's here and L's here. And the reason we have to decide that is because whatever goes on our y-axis, we're going to solve for so that we can graph the linear equation. So I'm going to solve for L. So to do that, I have to minus 0.75s from both sides. So I get 1.25L less than or equal to negative 0.75S plus 30. To get L by itself, what do I have to do? Divide by the 1.25. And make sure you divide everything by the 1.25. So I get
24.
L is less than or equal to 0.6S negative plus, you got 24, 30 divided by 1.25, 24. Just because I'm a mega awesome grapher, I'm going to convert the 0.6 into like 6 over 10. Because I want a slope. I'm going to graph this line. I want a slope that I can have a rise and a run for. So let's bring my graph down. All right, so I need my y-intercept is at 24. So I'm going to go 2, 3, 4, 7, 9, 12. Oh, I don't quite have enough for 24. I'm going to have to do it 1 for 1. I have to do it 1 for 1. Okay, so I go up to 24. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. So here's our starting point at 24. And I get that from my equation. That's my y equals mx plus b. B is the 24. And then my slope is negative 6 over 10. So I'm going to make that slope happen here. So I'm going to go down 6. What is negative 6 over 10 simplified? Just for fun, guys.
3/5, that's what I was about to say.
3/5. So technically we can go down 3 over 5. Let me make sure I'm talking correctly. One, 2, 3, 4, 5. You have to keep going. You have to keep going. Even though my graph ran out, I got to keep going because that is in my reasonable range. So I have to extend this out and keep going. All right, let's draw my straight line. We are included, so it's going to be a solid line. I'll make it periwinkle just for fun. Okay, so I have a solid line and I want everything below that line. So I'm going to shade everything below because it's all the L's that are less than or equal to. Okay. So now that we have it shaded, let's go ahead and look at what the question is actually asking. It says, use a graph. What are the possible combinations of small and large rides you can ride now? Well, definitely none. No large, no small, right? So this point right here is a point. I can ride what? 23 large ones and 1 small one. If I wanted to, I can ride up to, I definitely can ride 10 small ones and no large ones. So we have a bunch of variety of combinations. So that's why we have, instead of listing them all out, we say, here's our graph. This is at 24. I just want to mark that I'm counting by ones so that anybody looking at my graph can see I'm counting by ones. So there's a bunch of variety of, a bunch of different combinations of large and small rides that we can possibly have. Okay. Okay, so let's take what we were doing from before with absolute value and apply it to inequality. What? So we are going to graph y minus 4 less than or greater than or equal to 2 absolute value x minus 1. So if we are going to graph this, I definitely want to have y by itself, so I'm going to add 4 to both sides. And my lovely ladies and gentlemen, never, never, never can you distribute or take away anything inside or outside of the absolute value. So I can't add that 4 to the minus 1 in my absolute value. It just gets stuck on the outside. Okay, so we did these kind of transformations yesterday. So I'm going to throw, you guys do not write this down, because I'm going to throw down the parent function of an absolute value equation. So an absolute value equation has a V shape. Its vertex is at the origin. It has a slope the same as whatever value is in front of the absolute value. So this is y equals absolute value of x. So in this case, the slope is 1, so it goes up 1 over 1. So this is our parent function. We are going to take this parent function and apply all this shenanigans to it. So the first thing we're going to do is to move it down 4 units. See if I can move it. Sorry, up 4 units. Sorry, thank you. It's a plus. So we're going to move it up 4 units. Then we're going to shift it to the right 1 unit, because that's what that minus 1 does. Then the 2 says I'm going to stretch it vertically by a factor of 2. So we're going to take now, I have, this is the graph of y equals 2 absolute value of x minus 1 plus 4. Go ahead and write that down. I'm sure it's on your paper. The next thing I'm going to do is shade everything below, or sorry, everything greater than this graph. Everything above. So we're going to highlight and shade everything above the graph of this absolute value. Yes, please draw that graph. The only thing you don't have to write. Okay, so put this graph on your paper. What inequality does this graph represent? Definitely an absolute value inequality. So let's put the generic form. Here's the generic form with all of our transformations inside of it. And then we'll see how this guy gets switched around. So we have a dashed line and we have everything shaded above. So this is going to be y greater than or just greater than equals. I wrote them down. All right, so this isn't working. I just erased the equal to. All right, so I need to look at the slope of our graph to see if we have a vertical stretch or compress.
Community college fair.
Okay, so I know that usually if you look at your parent function, usually the parent function is on the origin. And I can see that this guy is shifted 2 units to the left. So I know that it's going to be x plus 2. That'll shift it 2 units to the left. I know that it is shifted up 1.5 units. So that means my k is a 1.5. And I can see that my slope is down 1 over 1. So the slope doesn't change except it is a negative, so it pops it down. All right, so notice right here that we're counting by 2s. So in fact, let's get a little eraser. So in fact, when we are not shifting over, we're shifting over 2 graph units, which is actually a total of 4. And we're shifting up 2 plus 1 more, which is 3 units up. And it's still, the negative will flip us upside down and reflects it so that it's a downward facing absolute value. And this is the equation of this line. We're still shading everybody above. And yeah, that's the end.